very interesting topic of process safety time in general, and just letting everybody know. A few years from now, we are not going to use the term process safety time. We're going to use MERT, which is maximum equipment response time. I will get into that because process safety time was poorly defined. The concept that says my safety function needs to activate faster than the process safety time is not specifically true, even though that's what the standard says, which is why we are rewriting the standard. Those of you that know me know that I've been sitting on ISA 84 since 1994. But I've also been, for the past few years, I've been actively involved in the IEC 61511 committee, which is a tighter group. I mean, yeah, you have to pay to be on the committee. The committee meetings are all over the world, so it's a lot more of a commitment to be part of that group. And anyway, that's something that we've been looking at. So what I'm going to do in this webinar is I'm going to jump around to a bunch of places. I'm going to look at the standard to see what process safety time means. Then I'm going to go look at some of the information that none of you have seen related to the internal machinations of the 61511 committee about why process safety time is poorly defined and how we need something better to where we can say that your SIP response time has to be faster than the MERT. And that's going to actually mean something. Then after we kind of talk about process safety time, we're going to kind of bring it back into the fired heater world. So those of you that know me also know that I wrote most of the technical report from ISA 84.00.05, which talks about basically it started out as selecting SIL targets for all the the typical fired heater safety functions, understanding what those functions are, what hazards they're trying to prevent, what actions you need to take. And something that we didn't do in release of the new version of the technical report that maybe we should have was talked a little bit more about process safety time. And then I'm going to kind of wrap it up with more of a process safety time workflow where I'm going to tell you that you don't want a precise number. You're wasting a lot of time. You're wasting a lot of money if you're trying to calculate a precise number. Furthermore, that precise number is a lie. It's an illusion. It's a fake. You're going to do a simulation. You're going to make a lot of assumptions in your simulation that probably are not true. No, they're definitely not true. And they could lead to results that are actually non-conservative. So a lot of stuff. Big discussion here. So I'm going to share my whole screen because I've got so much stuff going on. I'm going to pop over to this SRS presentation in a second, but let's just start out by looking inside a boiler, shall we? There you go. That's what we're looking at. That's a beautiful, beautiful flame. Kind of scary that you're all up in it like this, but what point I'm going to bring up in a few minutes is this is not a C-star. This is not a continuous stirred tank reactor. I don't know how many of you are chemical engineers, but as chemical engineers, when we were doing mass balances, we learned about the continuously stirred tank reactor, where when you inject something into it, as soon as you get into the reactor, everything is perfectly mixed. Which that kind of simplification, like the ideal gas, like the frictionless plane, is something we know is not true, but we kind of use it to allow us to do our work. And in the fired heater world, it's never going to be true. there's no amount of time that you can let stuff mix and it will all be equally mixed in the firebox. And I'll show you another CFD model that we put together. Well, we put together some CFD models for a customer of ours showing a leak of methane into a firebox. And I'll get into a little bit later why we did that and what problem they were getting at. Response time. All right, let's jump right into response time. So this is going to be kind of the starting point, and we're going to kind of lay down what are the requirements for process safety time in general? What are the definitions that we're using? And then I'm immediately going to pause and go back into what you're going to be seeing in the next couple years. And then once I kind of lay this out, then I'll go back and we'll start talking specifically about what does this mean in a fired heater? What is the consequence in a fired heater? How long does it take for that consequence development? And ultimately, what number do I put in my safety requirement specs for process safety time, and what number do I put in for the equipment response time? And you'll be surprised to learn that I'm going to tell you that 99% of the time you are not going to want to calculate the process safety time because it's a pile of assumptions, and generally your equipment is going to work way faster. So why don't we do the risk analysis thing and set some thresholds, do it qualitatively? We'll come back to all that. All right, let's start in. Again, this is the SRS training class out of the Connexus Process Safety Training Center. So a couple things as we start down this timing requirements issue. We're going to start out with some definitions. And then we're going to move into how do you determine what this number is for your particular plan. So we're going to start out with that definition of process safety time. And I have mentioned to you before that process safety time is a phrase that is going obsolete. Now, we didn't change the definition of process safety time because this is embedded. People have been documenting process safety time for over a decade, maybe over 2 decades. So we can't really change the definition. We needed to create a new one. So let's start with the definition itself. Process safety time is the time period between a failure occurring in the process or the basic process control system with the potential to give rise to a hazardous event and the occurrence of the hazardous event if the SIF is not performed. So it's basically how much time elapses between when I have my initiating event failure and when I have my consequence, when I have my explosion, when I have my fire. That's great. And we have been taught for time immemorial that your safety instrumented function needs to activate faster than your process safety time, which is true. It's always true. But it actually needs to activate a lot faster than your process safety time in a lot of cases, because there is a time that elapses between when my initiating event occurs and when my safety instrumented system knows that it has occurred. And you can't take credit for that amount of time when you're defining what your required safety function performance time, activation time is going to be. All right, note 1, right out of the standard, says that this is a property of the process only. So we're looking at the process, we're defining how the process behaves. The next part of the note says that the SIF has to detect the failure and complete its action soon enough to prevent the hazardous event, taking into account any process lag, such as cooling of a vessel. So that would be kind of in this note here. Think about a safety function where when you detect that the temperature in your reactor has gone high, you're going to want to flood a cooling jacket with cooling water to try to cool the reactor down. Well, it's going to take some time between when you turn your cooling water pump on and when you actually start to cool the process down. So those kind of process lags. Well, it turns out that there's a lot more lag than just the process lag. And I'm going to show you a graph, a chart that tries to list all these things out and lets you know what you can actually take credit for. All right, some other definitions, or actually it's not a definition, it's a standards requirement that says in clause 10.3, everybody knows that's the list of SRS items, that list of things that you need to document in the SRS to be compliant with the standard. It says one of the things that you need to document is the response time requirements for each SIF to bring the process to a safe state within the process safety time. And let me tell you, hear me now and believe me later, the next version of the IEC 61511 standard is not going to say process safety time. It is going to say MERT. And MERT is going to be maximum equipment response time. I was getting ready to write that up on the screen, but I won't. We'll get into that. Okay. And there's kind of the little extra piece of information here that's not specifically written into the standard that says that response time needs to include a lot of other items. There's this thing that I refer to as the PV reversal lag. So when you start injecting cooling water into your reactor, the temperature doesn't immediately drop. As a matter of fact, the temperature is probably going to continue to go up for a while before that cooling water takes effect. That's the PV reversal lag, and that's what the process lag here in note 1 of the process safety definition was talking about. There's also the PV detection lag, which is how much time elapses between when my initiating event occurred and when my safety instrumented system actually knows that it has occurred. So when we start talking about MERT in the next version of 61511, the MERT is going to basically, it's going to definitely pull this PV detection lag out. We're not completely done with the modifications. I think we need to talk a little bit more in the standard, maybe in the informative annexes, the part 2, about the, you need to consider this PV reversal lag also. Okay, so here is a graph, and I'm sure I'm not the only one who's done this. Pretty much everybody who fancies themselves to be a safety instrumented systems guru has a chart like this somewhere that they pull out when they're talking to customers and giving presentations. So let's do a deep dive into this chart to understand what are all the attributes of the historic process safety time, what is going to be included in the future maximum equipment response time, or MERT, and what do all these things mean? So let's start out by talking about these horizontal lines. These horizontal lines are operating limits of the process variable. So on the left-hand side, the y-axis is going to be the value of the process variable. Now, normally, there's going to be a normal operating range that you're going to be working in. And it's the job of the basic process control system to keep you in that normal operating range, or actually you can set the set point at different places inside the normal operating range. So that's where we're supposed to be. And if that is the case, everything is great. That's how we design the plant. That's how we want it to run. But there can be situations where we go out of control. And in this case, I'm showing a hazard as the process variable increases. We could do the same thing flipping this graph upside down, or actually, I could draw this with an upper hazard and a lower hazard, but that's just too confusing. I only put it on the one side to make it easier to understand. So if I lose control and my process variable starts to trend up. So let's go back to this reactor with the cooling water jacket on it. So the initiating event might have been that my reactant, so let's say I'm adding a reactant into this batch reactor and my valve failed wide open. So now I'm sending an uncontrolled amount of reactant into this reactor. That's going to make the temperature start to go up. Now, we're not going to know necessarily that the temperature is going up unless the operator is sitting there looking at that process variable, which is not very likely. They've got a lot to do. We're not going to generally know about it until we start approaching a safe operating limit. So the next line that I want to talk about is this one here, which is, okay, as long as I am below this safe operating limit, the line that's in yellow, my plant is just fine. I don't ever want to exceed the safe operating limit. But if I do exceed the safe operating limit by a little bit, nothing's going to happen. So you know that in a pressure vessel, let's say your maximum allowable working temperature or working pressure is 100 psi. Well, if you go to 110, nothing's going to happen. As a matter of fact, your relief system is kind of expecting that you're going to get up to 110. And you've probably hydro-tested your equipment up to 150%. So that safe operating limit, when you exceed it, it doesn't mean you're going to have a catastrophe. But in practice, we design our plant to not exceed that safe operating limit. So when I'm setting my set point for my safety instrumented system, I need it to be below my safe operating limit to the point where I know that even if my process variable continues to go up after I've activated my safety instrumented function, that I'm not going to violate that safe operating limit. Now, the last bit of this figure is the line on the very top. And this is the actual design limit. And I don't mean the maximum allowable working pressure. I mean the maximum hoop stress that thickness of metal is capable of holding, which is going to be significantly higher than the maximum allowable working pressure. So if you exceed the design limit, that's where we expect to pop this vessel open, to get our rupture, to get our actual catastrophe going here. So that hazardous, and that's where the hazardous event occurs. The hazardous event doesn't occur until we get that overpressure that causes the loss of containment. Now, for this hazardous event, when we're talking about a fired heater, the hazardous event is when most of the time, and there are two hazards of concern. Well, there's a little bit more than that, but let me give you the biggest concern in the fired heater. The hazardous event is when I ignite my gas cloud of unburned fuel that has developed in the fired heater, which is going to cause an uncontrolled combustion, which in a worst case scenario will be a deflagration in the fired heater, causing it to, and I hate using this term, explode. Now we'll soften this up a little bit later because most explosions in fired heaters are going to be very weak deflagrations that don't do a whole lot of anything. But in some cases, they can be very violent and actually cause the heater basically to collapse and fall over. So I'm going to come back to that. But that's the hazardous event that I'm talking about, the explosion, not when I start to put fuel gas into the fired heater. That's not the hazardous event. The hazardous event is the explosion, which part and parcel of that is I need to find a source of ignition, which is part of why it is insanely difficult. No, not insanely difficult. It's theoretically impossible to know the process safety time on a fired heater because you cannot know when it is going to ignite. But let me step back from that and come back here. Come back to our theory in our standards definitions. Okay, so we want to avoid crossing the safe operating limit. So we're going to set our trip point of our safety function to make sure that we can activate and consider a PV reversal lag to allow us to make sure that that process variable is going to change directions before I hit my safe operating limit, let alone get anywhere near my hazardous event. Okay, so those are the lines that are horizontal. Now let's talk about the lines that are vertical, which indicate points in time and also indicate time durations. The first item is the initiating event. This is going to be some sort of process failure, and I am including the basic process control system as part of the process. So it's not an SIS failure. It might be a BPCS failure. It might be a mechanical equipment failure. It might be a bunch of other things. So in the example of the runaway reaction because we lost cooling, or runaway reaction that I was just saying, there was a BPCS failure that caused an uncontrolled amount of reactant to start going into this reactor. Okay, now when the initiating event occurs, that's something that we might know about very fast, but it might be something that takes a long time to develop. So when I start pumping extra reactant into the reactor, the temperature, which is what we're worried about, is not going to react very quickly. Well, it might. It depends on the reactivity of whatever you're putting into this piece of equipment. But in the example here, you'll see that the temperature starts to ramp up kind of slowly. So there's a long amount of time that might elapse between when did the initiating event occur and when does my SIS know that the event occurred. This is the PV detection lag. The PV detection lag, classically, the way we've defined process safety time, the PV detection lag is included in the process safety time. But that time is not available to us as SIS engineers when we're determining how quickly the safety function needs to activate. So that's something that we're going to need to think about and we're going to need to throw out because it's not available to us. The other thing that we're going to need to think about is actually, but before I go to PV reversal lag, let me, right up here is the defined process safety time. So it's going to include not only the amount of time that it takes to get to the PV that the safety system is going to activate on, it's going to also include, well, how much more time do I have after I know that the SIS variable has been violated until I actually have my explosion, my loss of containment, my hazardous event. Now, when we've defined process safety time, we were defining it based on the hazardous event, not violation of the safe operating limit. So that's another area that we're going to want to tighten up on a little bit because we don't want to violate that safe operating limit. So if you look at the classical definition, and from the amount of time between when the safety instrumented system activates, the amount of time that we have before we exceed the safe operating limit is a lot smaller than the amount of, oh, sorry about that. Whoa. The amount of time that we have available before the plant blows up. So we're generally, as SIS engineers, not going to give ourselves that whole time slot for the safety instrumented function to activate. We're generally only going to give ourselves this little tiny time slot. Okay, continuing on. I talked about the PV detection lag. There's also this item down here called the PV reversal lag. And this considers the fact that even though my safety function activated, that doesn't mean that the process variable is immediately going to change direction. Now, sometimes it does. If my pressure in a vessel is increasing and I open a dump valve to dump it to atmosphere, that pressure is going to drop in a hurry. But in this particular case, and I've been using temperature a lot because temperature is really, really freaking slow. So those temperature safety functions are things you need to pay a lot of attention to. So in this case, when I activate my safety function, which is to flood a cooling water jacket with cooling water, I'm probably not going to know that the temperature is probably not going to drop immediately. The unreacted material reacting and generating heat is probably going to overpower the cooling water effect for at least some time, which is why you see this process variable continue to go up, maybe not at the same rate, but continue to go up before it eventually starts to go back down, which is what we're shooting for. Now, you need to think about how much is this variable going to go up during that PV reversal time lag to make sure that you don't exceed, definitely don't exceed your design limit. But I'd prefer you to not exceed your safe operating limit. Okay, so that's a lot of discussion of process safety time. And this kind of brings up, when you're looking at this, well, I need a SIF response time. And my SIF response time is going to be a little tiny nook right there. It's not this whole process safety time bin. That's not available to me. I want to know how much time do I have to turn around my safety function between when the PV violated the process variable And either when it's going to define the safe operating limit or when it's going to exceed the safe operating limit if you're really conservative, or by the standard when you're going to exceed that hazardous design limit. All right, so right out of the gate, now you should be thinking real hard about your policies and your procedures and your corporate standards, because if your corporate standard says you need to define a SIF response time that is less than your process safety time, no good. I mean, I just showed you that's not safe. That's not conservative. So we in the standards committee change things. So let me hit the discard button here. And all right, everybody be prepared. Now, I know that we're recording this and we're going to publish this on a podcast for everyone to look at. But I am going to show you right now some of the internal machinations of the IEC 61511 committee, how things work, and how we make changes to that committee. And it is going to be through the use of something called an information paper. So what I'm going to show you right now, and I'm going to try to protect the guilty as much as possible. Let's open this up. Okay, so this is an information paper, and what an information paper is someone suggested a change to the 1511 standard, and we flesh out what that change needs to be. We discuss it internally, we vote on it, we change it again, blah, 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 blah. So what you're looking at, we were working on this at our Krakow meeting in Poland last year. Title, SIF response time and Annex A guidance. And basically there's an abstract of what we're doing. And we basically said, well, we're looking at the definition of SIF response time in part 1. We're looking at the definition of SIF response time in Annex A. And it all started out with someone saying, hey, SIF response time doesn't have a definition. So in the next version of the 1511 standard, little secret, well, it's not a secret because I'm showing you, we're going to have a definition for SIF response time. Change history, rationale for making the change. So we said, well, basically someone on one of the national committees. So the ISA 84 is the national committee for the United States that contributes in the IEC 61511 standard. So there were 3 different national committee comments to the tune of, you guys don't have a definition of SIF response time in the standard. You should probably clear that up. And while we were in the process of clearing that up, we said, you know what? The definition of SIF response time is kind of sloppy. Maybe we should change it. And, long story short, we decided not to change it because there are thousands of companies all around the world that have SIF response time in their corporate standards and their procedures and documents. So we can't change it. So we had to create up with a new term called MERT, maximum equipment response time. So then basically what you're looking at, and you're going to see people in the standards committee over on the left-hand side, we kind of sketch out how do we want to change what's in the standard, and just a little bit at a time. So for SIF response time, this is all going to get added. Or actually, we're changing the definition, we're changing the note. And even the definition of diagnostics has changed to say that they need to be frequent in relation to the MERT, as opposed to frequent in relation to the process safety time. And then now we have this new definition of maximum equipment response time. So now when we're defining the SIF response time, we're going to want to make sure that the SIF will activate faster than the MERT. So what is the MERT? It's the time period for a specific hazardous event between the process reaching the safe operating limit and when the process will pass the never exceed limit if the safety functions allocated to protection layers are not performed. So key here is safe operating limit and never exceed limit. So the never exceed limit, that's the safety instrumented functions design set point. So again, so now we're basically saying that the MERT is the difference between this spot here, which is the SIS trip point, and this spot here, which is exceedance of the safe operating limit. And you see that that is tiny in comparison to the historical defined process safety time. So that's what's coming up in the next version of the standard. Now there's a bunch of other stuff that we played with in here, which, you know what? You're just going to have to wait till the next version of the standard is released to get into all those details. I've already told you too much. Okay, let's jump back in. Actually, let me erase what I just scribbled here before I jump back into the presentation. Now, some of the other things that you need to think about in this whole process safety time, maximum equipment response time, SIF response time discussion is time delays. So when you're defining a time delay, that time delay is part of the SIF response time. So if my sensor activates in 300 milliseconds, but I put a 2-second time delay on the safety function, it's not actually responding in 300 milliseconds. It's responding in 2,300 milliseconds. So time delays need to get added up and become another portion of your SIF response time, and you cannot exceed the SIF response time considering the time delays that you put in. Now, time delays are very valuable. They prevent signal noise from causing shutdowns, short duration anomalies from activating safety functions and potentially putting you into a more dangerous condition. Sometime you'll be able to perform a manual action if the process safety time is very large. And guess what? In a fired heater, there is something that has a very large process safety time, and that will be the amount of time that elapses between when you lose flow in the tube of a fired heater and when that tube ruptures. Again, that could be very, very long, but you know, every heater is different. So we'll get into that in just a second. So again, that time delay that you're putting in, do not forget that that is part of your SIF response time that you need to calculate and make sure that does not exceed that MERT or maximum equipment response time. All right. Okay, so I've got a couple more slides here, and then we're gonna go in and do a deep dive into the fired heater side of the fence. So you've got two options for setting your response times. The first one, which a lot of you, well, you know what? I could put another one down here that is guess. Because I was kind of in the back of my mind, I'm thinking, well, what is the one that's most commonly done in the process industries? And I hate to say it, it's probably this one down here. Someone was in systems integrator, instrumentation and control engineer was putting together the SRS and just threw a number down because they needed to get a deliverable out the door. How do you like that for scary? But hey, I'm just telling the truth. I'm just telling you what I've seen out there. Now, other than your systems integrator guessing what the process safety time is, let's talk about reasonable, rational ways to figure out what the process safety time. The first one is the fully quantitative. And being an engineer, engineers love them some fully quantitative. They love their spreadsheets. They love their simulation tools. And they're going to want to run calculations. The fancier the model, the better. Computational fluid dynamics, bring it on. But in reality, 99% of the time, you do not need to use a fully quantitative model. All right, so what do I mean by a fully quantitative model? Well, what you're going to do is you're going to calculate a time that elapses between when you get the initiating event, when you exceed your set point of your safety system, when you exceed your safe operating limit, and when you exceed your design limit. You're going to do that based on a dynamic quantitative process model. So as you've been designing your oil refineries or your chemical plants or your pharmaceutical plants, most of the time you're going to be using something like HISIS from Aspen. It is a process model. Now, most of the time, you're going to do it in steady state mode. But those models have the capability of going into dynamic mode. So I am operating at a steady state, and then at one point in time, I am going to change one of the variables and then watch in real time how all of the other variables change with it. Okay, now coming back to fired heaters, there are a few methods that you can use to do a dynamic simulation of what happens inside your firebox. The most sophisticated one would be to use computational fluid dynamics to look at what the fuel gas versus air versus flammable mixture concentration is inside the firebox after you lose your flame. Very expensive, very time consuming. The other problem with that is there is no consequence until you find a source of ignition. And it is unknowable to determine when the ignition is going to happen. So the best you could do is dynamically determine when I'm going to be able to get a flammable mixture. Okay. So once we do our dynamic simulation, we're going to calculate a SIF response time by summing the actual response times from vendor data. Don't forget to include the time delays and time constants for any smoothing functions that you've done when you're running those calculations. And then you're going to want to document all this on a per SIF basis. So for this fully quantitative, I mentioned the computational fluid dynamics approach. The other approach is going to be the C-star. Or a lot of times, if those of you who are chemical engineers, if you want to put a smiley face in the chat, we did this. The C-star, C asterisk. So that's the continuous stirred tank reactor. So in a continuously stirred tank reactor, I've got a tank and I've got a mixer. I've got a level in the tank. So I've got an input and I've got an output. Now, when I'm doing a C-star model, I am going to put a certain composition of material in, concentration 1, concentration 2, etc. And then I'm going to get a composition out based on whatever reaction I'm doing. Now, this reaction is going to come to steady state. If you change the input, you can create a quick and dirty spreadsheet. And back in college, that's exactly what we did. We created quick and dirty spreadsheets to see how the output changes as a function of the input. And this is really, really easy to do because if you remember your good old mass balance, what comes in has to go out. It's a little bit more complicated than that, but that's the equation that we're running. So kind of on a time-by-time basis, what did you put in versus what came out? Now, the problem with the C star is it assumes that the concentration inside that vessel is constant. It's perfectly mixed. As soon as you put something in, it's immediately quickly dispersed around the entire reactor, and thus what comes out is exactly what's inside, which magically immediately dispersed. So right out of the gate, if you're using a C star approximation to try to figure out how is the concentration going to grow, it's not going to be accurate because the material inside your fired heater is not well mixed. It never will be well mixed. You know it's not well mixed because, I mean, you know, again, feel free to give a thumbs up or a shout out. Have you ever had an explosion? And by that, I mean a puff or a woof inside of a fired heater while the stat gas was telling you that everything is okay. And that's because I lit one of the 12 burners, but one of the 12 burners flamed out, and that cloud from that one burner, when that methane mixed with all the other burners, when it got to the stack, everything was hunky-dory. But inside the firebox, you're concentrated, you found the source of ignition, and it lit off. So let's take a look at what I'm talking about here. So now I'm going to go back into my some of the things that I was playing around with in these are all YouTube videos. So this video is really neat. I'll let this run for a while. Somebody actually has a burner running inside, kind of, you know, what would be a traditional fire tube kind of heater, but they made their fire tube out of glass so that you could actually see what's going on. I don't know about you, but I want one of these for my backyard real bad. I mean, would this not be the coolest outdoor patio heater there ever was? Anyway, but I digress. So basically, what I'm trying to emphasize here with a real picture is you're not getting a consistent concentration inside the firebox. So the next thing I'm going to do is I'm going to show you, actually, let me cut this out. This CFD simulation. So now we're going to get into the world of CFD simulations, and we at Conexus, we know how to do CFD simulations. We do CFD simulations all the time. They are very expensive to do, and I'm going to encourage you not to pay us to do them. But before I get into the main CFD model, this one is really neat. What's going to happen is right now what we're modeling is these 5 burners are putting natural gas into this firebox. So this is a simulation of a piece of equipment at the University of Cincinnati. Now, right here, you're going to see a little discoloration. That's where we injected our spark into the CFD model. And what you're going to see is the flame that results from that ignition, and you're going to kind of watch how it moves through the firebox. So there's our ignition, and super slow motion, this is the flame front. Expanding in 3 dimensions, not uniformly, but expanding. And this is, you know, everybody's familiar with, I'm going to use burner A to light burner B to light burner C, and so on. So that's a CFD model of doing something that you should never be allowed to do. And here's another view of what's on fire, what's not on fire. So I thought that was kind of cool, but what I really want to focus on, let me stop that CFD model, is this one here, which is methane in cylinder. So basically what we're going to show is the CFD, and I'm going to pull up this simulation also to kind of show you what's happening to the methane in the firebox and why your C star is an approximation. And, you know, God love us all, us engineers, because, man, the more decimal points of precision I have in my spreadsheet, the happier I am. But we will always willingly turn a blind eye to the ridiculous amount of error that says even the first digit in that estimate is so far wrong that none of the other digits matter. All right, so let's take a look at what does it look like inside the firebox when you inject methane. Now, Conexus did a CFD model exactly like this for one of our customers who did something really stupid. They had a systems integrator who did a SRS for them. And in the SRS for the fired heater, that systems integrator did what a lazy systems integrator does. And they said, yeah, for your fuel gas valves, we want tight shutoff. So what does tight shutoff mean? Well, I've got a whole other webinar on that. Go check out our inventory, especially if you need professional development hours. To a lot of people, to most people, that means class 6. What does class 6 bubble tight shutoff mean? I'm going to use a soft seat. Well, this customer was a refiner, and I'm sure that all of you guys that are in the oil business, all the refining guys out there are chuckling about the idea of putting a soft seat into refinery gas service. So basically, they turned the heater on, stroked it once, and there was so much junk in the fuel gas built up on the ball that they just basically destroyed their seal, and they went from a class 6 to like probably a class 1 or a class 2 leakage rate after they stroked their soft seat one time. So what we did for them was we ran a model of leaking methane through the closed shutoff valves into a hot firebox. So the hot firebox is going to be the key, because it's really hard. Now, again, hear me now, believe me later. It's really hard to get a violent explosion in a hot firebox, because it's hard to get a big gas cloud, number one. Number two, the density of the gas is going to be a lot smaller because it's hot. And because it's hot, the differential pressure between the pre-ignited gas and the post-ignited gas ain't a whole lot. And if there's no pressure differential, there's not much of a shock wave, which is why everybody is so familiar with the puffs, whoofs, and bangs, but not quite so familiar with the explosions that cause that fired heater to blow itself apart and kill people. Not saying that they don't exist, but I'll go back to the situations where they do in a little bit more detail. So we ran a model, and that model, I couldn't find it, but it looked something like this. So let me kind of back up to the beginning here. So this is kind of like time zero. I've got my firebox, And now I'm going to inject methane into that. What does that look like? Stop my simulation. So for those of you that are looking at the model, what you're looking at, the color is the concentration of the methane. The hotter the color, the higher the concentration. It might be mole fraction because we're going all the way up to 1.0. So we might actually be looking at a mole fraction of methane. So those of you that are in the know also know that you're going to be at your LFL at around 5,000 ppm, 4,000, or that's 20% of LFL. Oh, I should have done all these numbers before I started. But basically, what you're learning is that right where you inject your almost all methane, then you have to mix with not oxygen, not even air. You're mixing with what's in the firebox, which is a lot of CO2, maybe some CO, and mostly nitrogen. Okay, so as this flame develops, what do you see here? As time progresses, nothing's getting mixed here. The fire heater was not designed to mix the flue gas. It was designed to get heat on the tubes. So it's not mixing. Don't expect it to mix. And as time progresses, you're seeing that this is what ends up happening. You end up getting kind of a smaller self-contained cloud. At no point in time is the entire firebox filling up with a stoichiometric mixture of fuel and oxygen. So what should we be doing? Let's go back. So from a precision standpoint, if I really wanted to do a quantitative analysis, I should be kind of looking at this gas cloud and figuring out how much time is it going to take for me to generate a gas cloud that is capable of exploding. What does it take for a gas cloud to be able to explode? Well, there needs to be a certain flame distance in the flammable region. So if you look where the gas came in, so let's just say the light blue is inside LFL. And let's say that the green is, now we're getting to the upper, or the yellow, we're getting to the upper flammable limit. So what I need to happen is I need for a flame to travel approximately 7 meters in order for the flame to go supersonic and cause a shock wave that's capable of causing harm. So doing some logic to figure out how long is it going to take before I have a gas cloud that's big enough, whether that's the size of the gas cloud or the flammable mass contained inside the gas cloud that's capable of causing an ignition, assuming that you're mixing with air, and you're going to be mixing with air. This simulation that they did, they just put methane in, which is why you're basically 100% methane. Right up at the top. Although I really don't know what these numbers are. They don't have a legend. The key point, C-star model, not going to be very accurate. And if you look, if you actually ran a C-star, maybe this gas cloud is big enough to cause an explosion, but look at all the blue over here. Look at all the blue over here. If I took all the methane that is in this gas cloud and smeared it out over the entire firebox, there's a very good chance that it would say, oh, you're below the flammable limit. When that is not true, it's just you're not at flammable everywhere. You're only flammable in certain spots. So this CFD type of modeling, very expensive, very difficult, very time consuming. What, Ed, do you recommend that I do instead of that? Well, I recommend that you do the qualitative process, which is why I went ahead and said that this is the best practice, there we go. Best practice. So what you want to do is you're going to want to generate your requirements for process safety time and equipment response times. And for those of you that know Connexus, if you've seen any of my discussions for SRS, you know that I am a big fan of general requirements. So I can one time in a general requirement say that my process safety time is always going to be less than 10 seconds. So sight unseen, you can just assume that the process safety time is going to be less than 10 seconds. Why did I pick 10 seconds? Because your equipment, your SIP response time also is usually less than 10 seconds, significantly less than 10 seconds. Most valves, so most of your valves are going to be under 6 inches or under. 6 inches or under, if you go with a conservative stroke time of 1 inch per second, that's going to be 6 seconds. Your PLC is going to turn around in a few milliseconds, a few hundred milliseconds. Your transmitter is going to turn around in a few hundred milliseconds. So about 7 seconds is realistic for what you can expect. So in this fully quantified, if you go to your process engineers and say, I need you to calculate a process safety time for me, they're going to spend hours running HISYS models to give you a number. And the number they might give you might be something like 45 minutes or 10 minutes or 1 minute. Okay, you could do that. But also, while you're in the PHA, while you have your HAZOP team together, you can simply ask them, while you're looking at the LOPA scenario for a hazard, you can simply ask them, how long will it take for this hazard to develop? Or even better, you can say, will it take more than 10 seconds for this hazard to develop? And 99 times out of 100, your LOPA team is going to say, oh, it's going to be like 10 minutes or 20 minutes. It's going to be way more than 10 seconds. Well, guess what? That statement, that qualitative statement from your LOPA team gives you, the equipment engineer, the SIS engineer, everything you need to know. All you know, all they've told you is that the process safety time is going to be more than 10 seconds. The MERT is more than 10 seconds. And as an engineer, you're going to look at your equipment and go, I know I can turn this around in less than 10 seconds. So why am I spending the time? Why am I spending all the money to go do a dynamic simulation when these two numbers, the MERT and the SRT, are qualitatively so far away from each other that the LOPA team can qualitatively tell me that they're separated? So that is what I strongly recommend. Set up a base, a kind of a baseline. Maybe 10 seconds is a little bit aggressive for you. Maybe you might want to put it to be 30 seconds. And then you define how quickly a typical safety function activates. Now, How have we dramatically reduced our work in this case? Because in this case, now all you need to do the quantitative approach for is if the LOPA team says, okay, I don't know if we've got 10 seconds. I don't know if we've got 30 seconds. So in that rare case where you're not sure how much time you have, that's when you're going to want to run these dynamic models. Okay. And also, so the additional work is limited to when your process safety time might be less than that general requirement, or when your equipment time might be greater than that limit. So if I'm trying to close a 72-inch valve, we ain't doing that in 10 seconds. Well, generally, we're not going to be able to do that in 72 seconds. So you really kind of limit the serious work to only the exceptions, not the bulk. The bulk of it, you're going to go, huh, I got a half hour, I've got 10 minutes, I know I've got more than 30 seconds. That's all you need to document. You could do that qualitatively. Okay. And then where do you document that for those? So for those of you that use the best SIS lifecycle tool in the world, that would be Vertigo. We have the general requirements. So that's where you would write a general requirement saying, okay, this is the equipment response time that I expect from all of my safety functions unless otherwise specified. Or you could do it on a SIF by SIF basis in the SIF data sheets. Then for the equipment response time, we do that on a subsystem by subsystem basis. So you spec out how much time does the sensor have, how much time delay does the sensor have, how much time does the logic solver have, time delay, how much response time on the final element and time delay, and then you add all those things together that are going to get you back here to this achieved response time. So that's what our recommendation is. All right, so let's go back a little bit now on the fired heaters. Look at the fired heaters in a little bit more detail. And I'm going to bring up, again, there's a whole 1 hour plus webinar on this topic, fired heater deflagrations, and why they're generally not as violent as you think they're going to be. And why, again, some of these C-star calculations, the assumptions are just, they're just, all right. I think I've pled my case there. Okay, so I'm just gonna kind of hit some of the high points here. So fired heaters, and you'll see I put explosions in quotes here. Actually, there we go. Yeah, if you don't operate a fired heater properly, you can get an uncombusted mixture of fuel and air that upon ignition can result in a vapor cloud explosion. Generally, these things are weak deflagrations. They're almost never a detonation. And if they are a detonation, they're probably going to be a weak detonation, not a strong detonation. And in order to cause a fired heater to collapse, now I am not aware of any instance ever of a fired heater exploding to where it threw shrapnel everywhere like a Hollywood explosion you would expect to see. The worst of the explosions caused a collapse of the structure of the fired heater, and it basically fell down. And unfortunately, it fell down on top of the people who were underneath it lighting it. Yes, Chris.
Okay, we got a question in the chat here. Any tips on how to expand this criterion to cover operator intervention response? And would a qualitative, experience-based gut feeling approach also be valid?
Okay, so on operator response. So since the question came up, I will just answer it right here. And I was going to drill down in a little bit more detail. Now, for a fired heater, there are multiple scenarios that we look at. There are scenarios that are loss of flame in a firebox that previously was at steady state. So the low fuel gas pressure trip, the high fuel gas pressure trip, the low airflow trip, those are scenarios where everything was operating fine, and then all of a sudden we lost our flame, but we are continuing to put fuel gas into the firebox. For that scenario, how much time do you have to respond? And the answer is you need to look at your flow rate that you expect. So what is the flow rate of the fuel gas going into the fired heater at that point in time? And then you take that flow rate and you determine how many seconds of that flow rate are going to be required until I have a gas cloud that's capable of igniting. Now, you might look at a flammable mass. So how many kilograms of methane do I need to have released before I have a cloud in there that's capable of ignition? Or you might want to combine that with kind of you might want to do some off-the-cuff generic CFD models to figure out how long will it take me to get a gas cloud that has a certain length to it, where if I ignited it, I would get enough flame speed to cause a detonation, which is generally 5 to 7 meters for methane in a 30% obstruction ratio, which technically you're confined, but technically you're not confined because your gas cloud isn't consuming the entire firebox. So that number, if you go ahead and run that number out, it's probably going to be somewhere between 5 seconds and maybe 20 seconds that you have before you get a gas cloud that's capable of causing an explosion under ideal conditions. So if I've got 20 seconds before I've got a flammable gas cloud, what is my MERT? What is my process safety time? Well, I don't know, because I don't know when that gas cloud is going to find a source of ignition. There might not be a source of ignition until that gas cloud works its way up into the stack. There might not ever be a source of ignition, and that methane could just go out the stack and waft away harmlessly for an infinite amount of time, which is why I'm telling you that the MERT, the process safety time, precisely cannot be known, because you cannot know when it will find a source of ignition. The only thing you can do to be conservative is assume that if I have a gas cloud that's capable of causing an explosion, I will assume that there is a source of ignition there that will cause, and now I want to set my SIF response time so that I can't develop a gas cloud that's capable of ignition. And that time frame is going to be somewhere in the 5 to 25 to 30 second range. Okay, so that's something you might want to, get out some spreadsheets, maybe run some you might want to play around with some fast models, although they're really not appropriate in a confined environment. They're only appropriate for outdoor releases. Or maybe, go run a quick and dirty CFD model. You can download Fire Dynamics Simulator for free. There's a steep learning curve. And kind of, run some numbers to figure out how long is it going to take you to get a cloud that I'm concerned about. Now, the other thing that you're going to want to leverage is API, NFPA are giving you numbers. They're setting times for your SIF response time, and you could probably safely assume that if NFPA or API tells you that they want that valve stroked in a second, you should probably comply with that and not so much worry whether my process safety time is 25 seconds or 30 seconds. If API tells you I need to stroke that valve in 5 seconds, you should probably stroke that valve in 5 seconds and be done with it, and go back to that PHA team and say, well, if I didn't stroke my valve in 10 seconds, is that probably going to be okay? And your PHA team is probably going to tell you that it will be okay. I assume we have another question, Chris.
Yeah, we have a couple more actually.
Okay.
PST should be much greater than 10 seconds, so we design the SIS to achieve better time than 10 seconds, correct?
Exactly. So you set a conservatively low process safety time that's lower than most of the process safety times for most of your SIFs. Then you set a high SIF response time that should be higher than most of your SIFs. And your workflow is just checking sure that to make sure you never violated the constraints, as opposed to trying to run precise calculations, which are generally not going to be worth your time and effort. Is there another question, Chris?
Yeah, what about detonation versus deflagration with more explosive fuel types than methane, such as hydrogen?
Hydrogen. Hydrogen is hydrogen's going to be more explosive, but at the same time, you're going to run into the same mixing and expansion issues. So let me come back to that in just a second, because I more on this is coming up. Okay. So yeah, go to the CCPS process safety glossary if you want to know what these terms mean specifically. Yeah, deflagration. Here's the definition of a deflagration versus a detonation. A little bit of information out of Lee's about differences between them from a mathematical perspective. So now this is my favorite, one of my favorite slides, because I kind of explain why a stick of dynamite is going to be a lot more dangerous than a combustion in a heater firebox. So if you take a look at my favorite condensed phase explosive, that would be trinitrotoluene, this guy right here. TNT, it's dynamite, as the boys in AC/DC used to say. Actually, they still say it. Some of them still say it, not the singer. Boy, I'm going off topic. Actually, this isn't, TNT is not dynamite. Dynamite is nitroglycerin mixed with a clay binder to kind of stabilize it. But I digress. Now, the important thing when you're thinking about a condensed phase explosive is it doesn't need oxygen. So when you ignite TNT, this molecule changes to these molecules because the product molecules are more stable than the source molecule. It's a decomposition reaction, kind of like what's happening sometimes in your lithium ion batteries, but I don't want to go too far off topic, and that's too far off topic. They're not burning, they're decomposing. So an explosion of TNT, you're decomposing the TNT into carbon monoxide, carbon, hydrogen, water, and nitrogen. And there's going to be potentially carbon dioxide and so on. So this came from a resource. I don't even remember what the resource was. But the point is, you don't need to mix with oxygen. Everything is there. And furthermore, 1 mole of my reactant gives me 7.5 moles of vapor product. And the vapor product is a lot hotter than the source material that we started out with. So when you ignite a TNT, you're getting just a pure volume increase is causing pressure to generate that shock wave, but the increased temperature is also generating that shock wave. Now, think about your typical fired heater where you're burning methane. So if I'm burning methane, I've got methane, and I'm going to bring in 2 oxygen molecules, which gives me 3 moles of reactants. That's going to turn into 1 mole of carbon dioxide and 2 moles of water. So 3 moles in the gas phase is 3 moles out in the gas phase. The only thing that's contributing to this pressure increase is temperature differential. Oh, well, that's interesting. So we're not getting an increase in the amount of gas. All that we're doing is making it hotter. We're making it a whole lot hotter, but we're only making it hotter. Now, this kind of goes back to why the explosions in the hot firebox are generally not that bad. Because if the firebox is already hot and I do this reaction inside a firebox, it doesn't get that much hotter. So the pressure doesn't increase that much. So not a whole lot happened there, which is why you get the puffs and the woofs and the bangs instead of the collapse. Now, what is the explosion that you do need to be worried about? And if you go back, look at the accident histories of fired heaters. The ones that are bad, the ones that kill people, generally started with a cold firebox. So I have a cold firebox and I didn't purge, or I purged too early, and I filled that cold firebox up with my fuel and methane mixture. Now, furthermore, the firebox doesn't have the same kind of natural flow that it does when it's hot. Think, if you've ever had a fireplace, when it's cold, it's kind of hard to get things going. You're going to smoke up your living room. But when it's hot, now you're pulling air through. So when you're cold, you're not pulling as much air through, which means your gas cloud is going to be bigger. It's going to fill that chamber a lot better. It's cold. And now when you ignite it, whew, you get that shock wave that goes from one side all the way through to the other side. The temperature increase went from room temperature, ambient temperature, all the way up to probably in excess of 1,000 degrees. That is the shock wave that can cause a heater to collapse. And you'll see that they generally happen only during startup for that I didn't properly purge my heater, filled up the firebox, and lit it off. That's the bad boy. That's the one you really need to worry about. And furthermore, your people are usually out in the field when this happens. And then the second one is when you have your loaded firebox. So that's the situation where I'm putting excess fuel gas into the fired heater. I can't consume it all. And I've got smoke. I've got carbon monoxide. I've got methane in the firebox. Now, what is my process safety time for the loaded firebox scenario? Well, this is kind of tricky because you have a hazardous condition. You have a fuel gas cloud that's capable of igniting before you do anything. So you got that high combustibles or low oxygen concentration in the stack. You're already in a dangerous state. but you didn't have a consequence. Why didn't you have a consequence? You didn't have a consequence because you've got no air. So you're not going to get an explosion in this situation until you give it air. How much time it expands, evolves, how much time before you give it too much air? Well, that's completely up to you, because giving it the air is the human activity. So that situation can exist for an infinite amount of time with no consequence until somebody makes the wrong move and gives it more air. So the amount of time for your safety instrumented to function responds, well, it could be infinity, or it could be, well, how long do you think it's going to be before someone sees a high combustibles, low oxygen concentration, walks out to the field and opens up the air doors on the dampers and blows it apart? Good question. And again, those are going to be a lot less violent than the cold startup firebox explosions, but still kind of something you need to worry about. All right, so yeah, I don't want to get into the weeds here. If you want to see more on this, there's a whole other 1.5-hour webinar on just this topic. But in a condensed phase reaction, all of the pressure gets generated instantaneously. When you're talking about a firebox explosion, your mass transfer limited. So this is awesome. If you want to have some fun, go out on the internet and look up this episode of Mythbusters where they try to create an explosion with sawdust. That's what you're looking at right here. They did. They made a log explode. Now, if you have a fireplace in your house, you know that if I light a log, if I can even get it lit, it's not going to blow up. The reason is combustion is mass transfer limited. The reaction will only go as quickly as you can get methane and oxygen to touch each other. So in the fireplace, you literally, the heat of the fire has to cause a cracking reaction to crack the cellulose in the wood into a vapor that's capable of burning. So if you look at a log on a fire, you'll see that there's a little area between the log and where the flame is. That's because the flame is causing a cracking reaction, and the gases that come off the cracking reaction are what is actually burning. Now, if you want to speed things up, shred that log into a super, super fine powder, mix it with air, or I'm sorry, mix it with oxygen and shoot it out a tube to get a nice, well-mixed gas cloud and ignite that. And oh boy, let me tell you, you will get a vapor cloud explosion. All right, so the key is inside your fired heater, that pressure builds up over time as that flame expands, as opposed to your TNT where everything happens all at once. The entire reaction in a microsecond, everything burns, whereas in a heater, only as fast as your flame front is going to expand is how quickly the pressure can build up. And if your flame speed doesn't go supersonic, probably going to be a whole lot of nothing in terms of the consequence that you end up with. All right, so yeah, I don't want to go into the weeds here talking about flame speed, flame velocity, effects of overpressure, but yeah, kind of summing it up, in a fired heater, it's a vapor cloud explosion. It's not condensed phase. Most of what's in the firebox is not going to burn in the first place if you're using air. Methane combustion doesn't change the moles of stuff in the firebox. So only the heat differential contributes to the explosion. And that will that also be true for hydrogen? So H2 plus O2, 2H2 plus 2O2 is going to give you, no, an H2 plus an O2 is going to give you 2 H2Os. All right, yeah, it's going to be equal molar. So yeah, you're not well mixed. You're not well mixed. You're not near stoichiometric. The combustible material only fills a portion of the firebox, not the entire firebox. There's not obstructions inside. Well, there are obstructions along the wall of your firebox. Well, I should be careful. You really need a lot of obstructions in your flame's path to be able to get that flame to go supersonic. And your firebox is going to collapse real quick. It's not going, you've got explosion doors. It's not going to contain enough pressure to really generate a lot of physical damage if your explosion happens when the box is hot. So if I could, let me just go ahead and go back to the conclusions where the rubber meets the road with respect to process safety time. I'm going to recommend that you kind of look at the qualitative approach. Set a qualitative limit for kind of a maximum or minimum process safety time or maximum equipment response time. In the LOPA, get the team to qualitatively confirm that that time is not being violated. Or if they don't want to confirm that the time is being violated, that's the time you assign a process engineer to figure out what the MERT or what the process safety time actually is. And it should only be for a tiny portion of your safety instrumented functions out there. If you do need to do a quantitative analysis, you have to do a quantitative analysis, but it should be a small portion. And the big kicker on setting this MERT is you know how quick your equipment can respond. Just ask the team, if you know your burner management system is going to turn around in less than 5 seconds, tell your team, do I have 10 seconds? Qualitatively, can you confirm that, yes or no? Document that in your LOPA, and you're good to go. I will go ahead right now and open up the floor to any other questions that anyone else might have.
Thoughts on documenting the process safety time as NA in the SRS, since we don't know when ignition will occur, and stating the response time of the SIF will conform to the performance criteria outlined in the appropriate industry standard?
You know, I have never considered that. That's not a bad idea, in that you're basically deferring to you're saying that there is an industry standard out there which is set my criteria, and I'm going to use that instead of running any other calculations. I mean, the other thing you could do is just set the maximum equipment response time to what the standard says you have to, your SIF needs to comply with, and just run it that way. I don't know how comfortable I am using not applicable for process safety time or maximum equipment response time. But I would definitely be comfortable just taking what came out of the industry standard and saying, this is my maximum equipment response time, with a note that says per API 556 or per NFPA 85.
Thanks again, everyone.